get sine of x all by itself. So add 2 to both sides. Gives you negative 2 sine of x equals 1. Divide both sides by negative 2, so the sine of x equals negative 1/2. Now, on your first rotation of the unit circle, okay, there's, again, a lot of this intangible, not able to be well documented work and thought in these. So we're looking for where are the angles that have a sign that's first and foremost negative. So when you start rotating around your unit circle, what's the first quadrant? Positive, so sine of x will not equal a negative there. What's your second quadrant? Positive, all students, so we're not going to be in there. We are going to have an angle in our third quadrant because only tangent is positive there, so sine is negative. So we are going to have an angle in our third quadrant. Then you need to think, again, it's not really something you can document because you just should know the value. What is the reference angle that has a sine of 1/2? Pi over 6. So that's pi over 6 in the third quadrant, which is what? 7 pi over 6, because this is 6 pi over 6. That's the best I can do to document that work. That's just a lot of thought. I will, and we can. I'm just going, because most often though, Josh, you can't, because most often they will restrict your interval. So if I take my third quadrant angle, that's 7 pi over 6 is a solution. And then I also have a fourth quadrant angle. Now if I'm staying between 0 and 2 pi, I can't use negative pi over 6. So let's just, for the sake of doing one full rotation to make sure we cover everything, let's stay between 0 and 2 pi. So what would this be? 11 pi over 6. So those are two solutions between 0 and 2 pi. But this one doesn't tell us that x has to be between 0 and 2 pi. This says x can be anything. So we have an infinite number of solutions here. Liam? Does anybody remember how we handled that? How do we, if we know that this is one solution, and any coterminal to that is also going to be a solution, how do we address the infinite number of solutions that are coterminal to 7 pi over 6? How do you get any coterminal angle to 7 pi over 6? What if we just wanted one other one? Add or subtract, well, 2 pi. For the record, I'm glad you said 360, because unless it otherwise specifies, all of your answers are going to be in radians. Okay, so keep your answers in radians. So add or subtract 2 pi any number of times. So your solutions are that x equals 7 pi over 6 plus 2 pi k times, where k is an integer. So you could add 2 pi one time, you could add 2 pi 2 times, you could add 2 pi 3 times, and that's going to give you your infinite number of solutions that coincide with the 7 pi over 6. And since k is an integer there, k could be a negative number, so you could actually subtract 2 pi once, or subtract 2 pi twice, and go backwards. So that's the infinite number of solutions that coincide with 7 pi over 6. We also have the infinite number of solutions that are going to coincide with 11 pi over 6. And so we have given all solutions to that problem. Now, a couple things. Thinking that this is what we're solving, and thinking about why are there an infinite number of solutions, if I just think about my sine paragraph for a minute, which is a cycle and goes on forever, negative 1/2 is right about here. And so can you see visually why we're going to have an infinite number of solutions? Okay? So that's the infinite piece. Now I also, and maybe I'll save this point for, no, I'll do it now just to get it over with. So this one, again, didn't restrict our interval. But most of them will between 0 and 2 pi. And there will be a point in time where you'll need a calculator because they'll give you sine of x equals 0.9 or something. And you don't know that memorized value. So let's pretend for a minute that they're asking for solutions between 0 and 2 pi, yet pretend also that we don't know the memorized value, so we need a calculator. So if they want the answer between 0 and 2 pi, my mode needs to be in radians. It is. And then I would do inverse sine of negative 1/2. Now, from last chapter, though, we learned that when we do inverse sine, it's always going to give us an answer between what and what? Negative pi over 2 and positive pi over 2. This particular one is going to give us the one between negative pi over 2 and 0, correct? Because it's our fourth quadrant. But that, when we get it, is not in the proper interval that this wants us to solve for x. So when we do this, it's going to give us what is technically negative pi over 6 radians. Let's just check that. Okay? It's going to give us that, but we can't use that answer because that answer is not between 0 and 2 pi. Yes? So we would have to add the full circle onto this in order to get an answer that is between 0 and 6.28 radians. So if I add 2 pi onto that, now I have the answer that's in the right interval for the solution of the problem. Okay? So when we get to some calculator questions where we have to use the inverse button on our calculator, we need to keep that in mind because often, especially with sine and tangent, cosine will be fine because inverse cosine gives us between 0 and pi anyway. That's fine. But inverse sine and inverse tangent give us between negative pi over 2 and positive pi over 2. If our answer is between 0 and positive pi over 2, we don't have to worry about this. But if the inverse sine or the inverse tangent gives us an angle between negative pi over 2 and 0, that's not going to be in this interval, and we're going to have to add 2 pi on to get the proper final answer. Do we follow that? Okay. So again, a lot of intangible, can't really show your work, have to think through it, thoughts that go into this. All right, so those are just some of the twists you'll come across. Moving forward, all of these are just give me the answer between 0 and 2 pi. So on number 2, let's think about it graphically first before I show you algebraically what happened here. Typically, our asymptotes are at, and we're just looking 0 to 2 pi here, are at pi over 2, right? But this has been compressed by a factor of 3. So we don't have an asymptote necessarily at pi over 2 anymore. That pi over 2 asymptote just got condensed. We normally, between 0 and 2 pi, have an asymptote at that pi over 2 and 3 pi over 2. So normally, if we were just looking for where the tangent of x equals 1, we would have how many solutions? We would normally have 2. Since we've compressed this by a factor of 3, we're going to have 3 times the number of cycles between 0 and 2 pi, right? which means we're going to have 3 times the number of solutions between 0 and 2 pi. We thought we had 2 solutions just based on tan of x equaling 1/2. We're now going to triple that number of solutions because we're going to have triple the number of pieces all condensed further in. So I think, just so we could see in the calculator, if I do my window from 0 to 2 pi and do -5 to 5 should be plenty. And if I type in the tangent of 3x, I'm in radians, so I'm good. I'm going to have triple. There's 1. Now it's doing the second version. Now it's going to do the third cycle of this. So I have triple the amount when I horizontally compress. So now my solutions at 1, I have 1, 2, 3, 4, 5, 6, 6 of them. I had 2, it looked like. I just tripled the number of solutions by having that happen. Okay? So hopefully graphically you can see what's going on. Algebraically, the fix for this is quite easy, actually. So if we are kind of tripling our x, and tripling our number of solutions, we're just going to multiply by 3, multiply by 3, multiply by 3 here, so that we can find what 3x has to be between. If x had to be between 0 and 2 pi, 3x has to be between 0 and 6 pi. So we need to find all of the moments that the tangent of this 3x equals 1 between now 0 and 6 pi, which means if we think about our unit circle, we're going to go around not once, not twice, but 3 times. And think about, in those 3 cycles, how many different locations does the tangent equal 1? So starting around our first, do we have anything in the first quadrant? Yes. What's the reference angle? Pi over 4. So 3x could equal pi over 4. Do we have anything in the second quadrant? No. Third quadrant? Yes, because tangent is positive 1 somewhere in the third quadrant. What's the angle? Right, I'm going to label this 4 pi over 4. So my third quadrant angle is 5 pi over 4, so 3x could also equal 5 pi over 4. And do I have anything in the fourth quadrant? No. And then that just gives me 0 to 2 pi, but I'm going that 3x could be between 0 and 6 pi. So I go around again. So I'm going to hit another one in the first quadrant. What's going to be the angle there? 9 pi over 4. What's going to be my angle here? So here, watch how I count here. 4 pi over 4, 8 pi over 4, 12 pi over 4, so this is 13 pi over 4. 12 pi over 4, this is going to be 16 pi over 4, so what's the next one? 17 pi over 4. I'm running out of room. I'm leaving that space for a reason. And then, so this was 16 pi over 4, this is going to be 20 pi over 4, so this is, I'll put it up top because I'm running out of room. And then by the time I get back over here, I'm at 24 pi over 4, which is at 6 pi, so I can stop. Yes? And so then I've got these 6 solutions to solve for x now. And when I do that, since I made 3x have to be between 0 and 6 pi, when I divide all of these by 3, going back to my actual x solutions, you'll see that all of my x solutions are between 0 and 2 pi. So when I divide all of these by 3, what's that just going to do to all their denominators? What's 21 pi over 4 when I divide it by 3? Keep, change, flip means I'm really multiplying by 1/3. So what's going to happen to all those 4 denominators? They're all going to be over 12. So 21 pi over 12, pi over 12, 5 pi over 12, 9 pi over 12, 13 pi over 12, and 17 pi over 12. And all 6 of these answers are, in fact, between 0 and 2 pi. So, in summary, when there's a horizontal stretch or compression, you need to kind of adjust the original x interval accordingly. And it's really easy. If it's 3 times x, then just do 3 times that. And then you have to set up all of your possibilities for when the tangent equals 1 between that new interval. Okay? The next one, yep. Say it again. I guess I do not think I understand your question. How would you do it? Yep. Mm-hmm. I need all of the, when someone says to solve something, they're telling you to give all solutions. This particular is just wants all the solutions for x values between 0 and 2 pi. Because if I didn't have this interval, there would be an infinite number of solutions. So they restrict it, so I only give a finite number. Did that answer the question? Sorry. Next one. Also change it. It's not just the sign of x. It divides x in half. So all I need to do over here is divide all of these in half. So that I realize that the x over 2, which is what I'm taking the sign of, I'm really only looking for values between 0 and pi here. So this is going to give me fewer solutions than I would have originally had if I was just taking the sign of x. Because when you divide this by 2, you're actually stretching out your sign. Give me 1 second, Stephen. So I'm only looking for any sign value that equals root 3 over 2 between 0 and pi now. Do I have anything in quadrant 1 where the sign equals positive root 3 over 2? Yes. So x over 2 could equal pi over 3. Do I have anything in the second quadrant? Yes, because sine is also positive there. So what would be the angle in the second quadrant? 2 pi over 3. So x over 2 could also equal 2 pi over 3. And then I'm done with as far as I need to go around the unit circle. So this angle here could equal pi over 3, or it could equal 2 pi over 3, and the sine of it will give you root 3 over 2. So now I just need to solve for x. I multiply by 2 on both sides. And so the x solution is actually 2 pi over 3 and 4 pi over 3. And again, if I kept going and found like, let's say, coterminals to any of these, they would be out of my 0 to 2 pi range. So they'd be too much. Think about your, I'll just give you the image, sine of x over 2. And I'm looking at a window between 0 and 2 pi. I only need to see negative 2 to 2. That's too much. and I'm looking for all of the places, and let me go back, where this graph is going to cross the horizontal line, root 3 over 2. So because my sine graph got horizontally stretched, I'm only seeing a portion of the sine curve. The rest of it would kind of come down and off the screen. And here's my line, root 3 over 2. And so between 0 and 2 pi, it's crossing twice. And we, of course, got those x-coordinate values. Okay? Any questions on that? Okay. Here's a totally different style, a quadratic. We are going to factor this just like we would factor anything else. It's equal to 0. So we're going to sort of guess and check. One of these has to be 2 cosine x. The other first term has to be cosine x. Your last and your last need to multiply to be 1. So there's only one way that can happen, 1 and 1. One has to be positive and one has to be negative, obviously, to make negative 1. And your outer and your inner needs to combine to be plus cosine x. So where does the positive go, in the first binomial or the second? So you want plus minus, yes? So let's check that. 2 cosine x times cosine x give me 2 cosine squared. So first and first works, last and last. Positive 1 times negative 1 gives you negative 1. That works. So if I do my outer product, what is that? Negative 2 cosine x. What's my inner product? And negative 2 cosine x plus 1 cosine x is... That's not right. Should have been the other way around. Your middle term is positive. So you want your positive sign to go with the larger of the products when you're looking at your outer and your inners. So that works, yes? Equals 0. What do you do when you're done factoring? Tee it up. So 2 cosine x minus 1 equals 0, or cosine x plus 1 equals 0. So when I solve this one, I'm going to get cosine x equals a positive half. And when I solve this one, I'm going to get cosine x equals negative 1. So if we think of our unit circle, having to go between 0 and 2 pi, we'll start with the equation on the left. As I go around my unit circle, do I have any solutions in the first quadrant? Yes, cosine is positive in the first quadrant. What's the reference angle? Pi over 3. Do I have anything in the second quadrant? Third quadrant? Fourth quadrant? Yes. Cosine is positive again in the fourth quadrant, so cosine will equal a positive a half. And since I'm dealing with a reference angle of pi over 3, I'm thinking of this as 3 pi over 3, and I'm thinking of this as 6 pi over 3, so what's the fourth quadrant angle? 5 pi over 3. So there's 2 for this one. And what is the cosine at 0? 1. So where is the cosine going to be negative 1? Pi. And those are your 3 solutions between 0 and 2 pi. Did you have a question, Stephen? That was a while ago and I forgot about you. Okay. Okay. On number 5, we could still factor. It's the difference of perfect squares. Or you could just add 1 to both sides. Divide both sides by 4. Square root both sides. So the sine of x equals plus or minus what? 1/2. So we have positive 1/2 and negative 1/2 to solve for. So we're going to have something in every single quadrant here, yes? What's the reference angle? Pi over 6. So what's my first quadrant angle? I'll just do this. What's my second quadrant angle? Because if it's 6 pi over 6 here, what's my second quadrant angle? 5 pi over 6. So those are my two positive half answers. But when sine of x equals negative a half, that's going to give me what in the third quadrant? 7 pi over 6. And what in the fourth quadrant? 11 pi over 6. So those are my four answers. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. That's accounting for my two positive a half options and my two negative a half options. Good? Any questions? And then number 6, which is the first time we're seeing this, but we have a combo of sines and tangents. So this particular one, I'm going to get equal to 0. Oops. And I'm going to factor. When you know how when you're solving an equation, if you ever divide by x and divide by x, you're losing a solution? You would lose solutions if you did that. So I am going to divide it out, but it's going to be by factoring. So I'm going to take out a GCF of tan x minus 3. And I need to tee it up, and that tangent of x equaling 0 is going to give me a couple solutions. So tan x equals 0. This one's going to give me sine squared x equals 3, which I'm going to have to square root both sides, so I'm going to get the sine of x equals plus or minus root 3. So starting with your tangent of x, when does tan equals 0 in the unit circle? 0, tan of 0 is 0, and pi. So x could equal 0 or pi. When does the sine of x equal root 3? It doesn't, Adam. Share. Why? Sine has a range of -1 to 1. So the sine of what angles here will ever equal root 3 or negative root 3? Right? Won't happen. If I do inverse sine even on my calculator of root 3, that's a number that's out of the domain for inverse sine, right? Inverse sine you can only take of numbers between -1 and 1. Root 3, root 2 for that matter, are all over 1. You get an error on your calculator even if you have it, because this is out of domain. So this provides no solutions. So you only have 0 and pi. Jalen. It wasn't tan cubed, where it would drop to a 2. This is just like, yeah, it's just like a minus 3x. If you factor out an x, it's just the minus 3 that's left there. I think you're thinking if it was tan cubed and I took out a tan, it would drop to a tan squared. That's not how the coefficients work. Okay? How do we feel about that? I like it. I like solving trig. It is better than proofs, yes. These are some of the techniques. Factoring, solving by square root you can do. Don't forget your plus or minuses, because stop moving around, you're making me nervous. When you take the square roots, don't forget about your plus or minuses, because that doubles the number of quadrants that you can work in. So that's like a little tricky thing. Obviously, FOIL factoring, GCF factoring, and then 2 and 3, the changing of the interval really is a tricky concept, but I think it's got a pretty easy fix. And then you kind of get your answers for what 3x could equal. You get your answers for what x over 2 can equal, and then you solve for x once you have those. I want to show you, and I showed it to one class, but I don't think it was yours, so if I am repeating myself. Just in light of prepping for the test later this week. By the way, if anyone knows in advance they're not going to be here on Friday, you need to take the test before you leave on Thursday. You can take it in class on Thursday if you want. Like, I can send you to a different room, because we're doing 2 days of review. You really only need one. You will be ready for the test by Thursday if you study to be. So we'll figure that out, Taylor, what works. If you don't want to miss class and you want to take it later in the day on Thursday, that's fine. Yeah, that's fine. Okay, so this is on, and you can write this down, this is on page 577. It's guidelines for verifying trig identity. So it gives you, have I showed you this? It gives you just different things to try. Like, there's no black and white answer for how to get things to prove out, so to speak. But it says to work with each side of the equation independently of the other side. So you can't add 5 to both sides. You can't cross multiply. You have to, whatever you do on the left side, you have to just exclusively be simplifying or manipulating on the left side. And then that is one side. Then you also exclusively simplify on the right side, but you can't add the 5 to both sides or do any sort of solving technique. We've talked about that. Then analyze the identity and look for opportunities to apply the fundamental identities, meaning look for opportunities for substituting in, maybe sine over cosine for tangent, maybe a Pythagorean identity. Look for opportunities to substitute things out and plug other things in so that simplifying kind of can unfold from there. And then just generally speaking, here are some of your techniques that we worked with. Rewriting things in terms of sines and cosines, which can sometimes get a complex fraction, which allows you to keep, change, flip, or clear fractions that can clear a lot more out than you anticipated. Factoring out GCFs. You've seen a lot of factoring in general when we're simplifying, which when you factor out something, what's left might be a Pythagorean identity that can now be substituted for. Splitting up fractions. So if you have a binomial over a monomial, we did a lot of A over C plus B over C, and some things might simplify out that way. Combining fractional expressions, so like getting a common denominator and adding fractions. We've seen examples of all of these. Multiplying the numerator and the denominator by a binomial factor that appears on the other side. So something like this would be like something if we were asked to prove this. If you have a fraction on both sides and you're trying to prove this, one of the techniques we can use is, okay, we could multiply this side by this denominator, 1 plus cosine alpha over 1 plus cosine alpha, and kind of see what that creates in the numerator. And on this side, sine of alpha, and see what that creates in your numerator, and gives you opportunities to substitute with Pythagorean identities. That's also kind of getting a common denominator on the left side and on the right side. One thing that's not there is the thought of multiplying by conjugates. So like if you see a binomial, just if you want to play around and see maybe this helps something come up, multiply by 1 minus cosine alpha over 1 minus cosine alpha. because when you multiply by conjugates, you usually get the difference of squares, which ends up often being like a Pythagorean identity substitution. So just a nice, I guess, summary. And then this last point, don't be afraid to stop and start over again if you're not getting anywhere. Unfortunately, that can happen. You do something, you get stuck, you just might want to start over. Liam? Only, yes, the sine and the cosine ones, the ones that on your reference sheet say memorize. So when you receive this with your test, it's going to look like this. You can just write them in. And if you want to at the top, you could also just write in your Pythagorean identities, because those aren't there either, just so that they're like physically in front of you. I think that's helpful, yes. I think there might be one other thing that this is on page 596. It's got all your, but that's your reference sheet anyway, so never mind, that's not very great. So that's it, just a little thing in the book to help you.